In this video, we continue our look at infinite series, and in particular, we're going to look at an explanation of the concept of partial sums. Now, an important component of series is the concept of partial sums. So to help us understand partial sums, let's consider the following infinite series. This is the infinite series of 6/10ths plus 6/100ths plus 6/1000ths plus 6/10,000ths, etc., etc., etc. But let's actually take a closer look at this infinite series. Now notice this infinite series is made up of a set of infinite terms where a sub 1 is the first term, which is 0.6, a sub 2 is the second term, which is 0.06, a sub 3 is the third term, which is 0.006, etc., 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 all the way down to a sub n. And a sub n is the nth term in the series where we have n minus 1 zeros followed by a 6. So it's 0.00000 all the way till 6. Corresponding to this infinite series is what we call partial sums. So S sub 1 is said to be the first partial sum. First partial sum. And what does that mean? Well, that's the sum that comes from taking the first term in my series. So S sub 1, the first partial sum, is simply a sum of the first term, which is 0.6. S sub 2 is said to be my second partial sum. And that's the partial sum that comes from taking the sum of the first two terms. That's 0.6 plus 0.06, or 6/10ths plus 6/100ths. And if I add those two terms together, notice I get 66/100ths, or 0.66. We can continue looking on at the rest of the partial sums. So if we have the third partial sum, S sub 3, that one is 6/10ths plus 6/100ths plus 6,000ths, and if I add up those three terms together, notice I get 666,000ths, or 0.666. Oh, and there's a typo on this one, see it? So down here, I have my fourth partial sum, and do you see my typo? So if I add up those four terms, the first four terms, of a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, I actually should get 0.6666, right? That's my fourth partial sum. So, in general, the nth partial sum consists of adding up the first n terms in my series. So I'm trying to spell and talk at the same time, but here I have my nth partial sum, and that consists of adding up a1 plus a2 plus a3 all the way down till a sub n. Now, if you take a look at these partial sums, you might start to see a pattern. Do you see our partial sums? And in fact, do you see the pattern? Could you tell me where these partial sums are heading? In fact, I'm inclined to say that if I was to take this series, this infinite series, 0.6 plus 0.06 plus 0.006, etc., all the way to infinity, don't you see that this is actually going to head towards the number 0.6666666 as I go to infinity, where those sixes just never stop and keep getting added? Or if you like, wouldn't you say that this converges to the number 0.6 with the bar on top? Or in other words, that's the fraction, what, 2/3? Do you recognize that as 2/3? Those partial sums kind of show a pattern, and in fact, they help us to see that this infinite series actually converges, and when it converges to the number 2/3. So now that we've looked at kind of a specific example involving partial sums, let's take a more general approach. Let's look at the formal definition for the partial sum of a series. So now this is our symbols and our math language. Definition: the kth partial sum of a series S sub k is defined to be as follows. If we have an infinite sum described by the series a sub n, where n goes from 1 to infinity, then S sub k denotes the kth partial sum of the series. And in fact, if I wanted to use sigma notation, I could represent S sub k as the sum of I could say n equals 1 to k of a sub n. That would give me the first k terms added up together to give me the kth partial sum. Moreover, if we looked at those partial sums and arranged them as a sequence, like we did with the last example, we get what's called the sequence of partial sums. And like we looked last time, if those sequence of partial sums form a pattern, or in other words, if they converge, then we say that the whole series converges. So in fact, if the limit of these partial sums converge to some finite number s, then we say that the sequence of partial sums converges, and hence its associated series is also said to converge, which was what we saw with our example. However, if the partial sums do not equal some finite number s, then we say that the sequence of partial sums diverges, and hence the associated series also is said to diverge. Now, it won't take long, but soon you'll discover that it's difficult, if not impossible, and time-consuming to find sequences of partial sums for infinite series. It's a difficult task. So generally, we don't spend the time finding sequences of partial sums and then evaluating the limits of those sequences to determine convergence or divergence. Instead, what we're going to be doing is collecting a bunch of tools that we're going to put into a toolbox. So we're going to use a toolbox of different tests that will help us to determine whether a series converges or diverges. In fact, the remainder of the chapter is going to be devoted to developing and practicing that toolbox of tests. This being said, there are two specific series which we can use the sequence of partial sums to assist us in determining whether the series converges or diverges. And those two specific types of series are what we call telescoping series and geometric series. And in fact, these are the types of series that are going to be the focus of our next two videos.